We are now going to talk about one very useful aspect of that is often integrated into microcontrollers called analog to digital conversion. The first question is, what do we mean by analog, right? Analog in general refers to things, we are using it to refer to things that are continuously variable, right, as opposed to digital, which usually switches between 0 and 1. I mean, they are essentially binary, they have two different values that they can take, whereas analog can take on a range of values, right? Now, what does that mean? Where would you actually come across something like that in real life? Everywhere, right? So you could start with something like, maybe you have a temperature sensor, which could be a thermistor, which ultimately sort of says that, the resistance of that block or the current that passes through it is going to be related to the temperature of the system. You could have light sensors, which basically generate some kind of current that's related to how much light is falling on the sensor. There are pressure sensors, which are usually on the principle of piezoelectricity, where the amount of pressure that's applied will change the voltage current characteristics of the system. Humidity sensors, force sensors, gas concentration, sound, right? At the end of the day, sound is a real physical quantity. It's measured using microphones. What does that mean? A microphone has some kind of mechanism that takes the sound waves and converts them into varying currents, right, or voltages, which in turn can then be sort of digitized, as we'll see later, and handled inside your processor. But the signal itself is an analog signal. Position sensors, right, things which are actually looking for how much have you moved, how far have you moved in a particular direction, are usually also analog. Things like acidity sensors, pH sensors, right, moisture sensors, all kinds of things that you use in the context of agriculture, farming, soil management and so on, most of them are dealing with analog quantities. So what that means, in other words, is that if you would like your microcontroller to talk to this outside world, you need some way by which these things can somehow be converted into a form that the MCU can interact with, right? So the problem over here is that the MCU, the core of the MCU, the CPU, the processing unit, doesn't work with analog values, right? It only works with numbers as long as they have already been converted into binary form. So what that means is we basically need to take our analog values and convert them into binary before we try to make use of them. And a common way by which this is done is to say that, look, I had some kind of an analog signal, which may be this orange curve that we have over here, right, is the actual nature of the analog signal, but I can't store it at every single point over there. What I'm going to do instead is look at what is the value at this instant of time, then again look at the value at a certain later instant of time, this one. Basically what I'm doing is sampling, right, rather than trying to somehow tell me exactly what the value is at every single instant of time. I'm making the assumption that if I have sampled often enough, I will be able to answer the question. If you ask me what was the value at the instant 1.267395 seconds after the system started, I don't know, but I do know what it was at the point 1.23 and 1.24 seconds, and from there I can sort of make an interpolation and say, hey, it was probably close to this, right? So I don't really know the value at each and every instant of time, but I know it at sufficiently many instants that anything else I can kind of interpolate and tell you what the value was probably close to, right? Now obviously there is a problem, potential problem there, as you can see, for example, in something like this, right, the actual signal dipped and then went back up, but there is no way that I can store that information by just having these two values out here, right? So what should I have done? Should I also have sampled at this point? Then maybe at this place I would suddenly find that, hey, if I actually also sample over here, it's a waste, because it's not really telling me anything extra about what's happening. Now there's a lot of theory behind how this works, and in fact in a signal processing course you would learn a lot about how to go about deciding what kind of sampling needs to be done and so on. But there are some fundamental principles that govern how to go about deciding this. Out of scope of this particular course, so for now we are just going to say that you need to understand that sampling means taking a real world analog signal and converting it into a set of numbers at different instants of time. So that's discretization, right, in time. You are making it discrete in time. You are sort of breaking time into discrete steps. Now, that's not the end of the story, because after all, like I said, what gets stored inside a CPU is not a real valued number. It is an approximation to a real valued number based on a certain number of bits. I might store an 8-bit value or a 16-bit value or a 32-bit value, but for example, I can never store the value of pi, which is an irrational number with an infinite number of digits, exactly. Right? There is no exact way of storing that in a digital representation. I may be able to store it up to 3 decimal places or 10 decimal places, or if you absolutely want it, you can store pi to 100 decimal places or even to 1,000,000 decimal places. The point is, you will need a number large enough to store that many decimal places, and still the million plus 1th place is a round off. There is a round off error out there, right? So rather than worrying about all that, what we instead say is, hey, we know what kind of signals we are dealing with. Let's decide on something which basically tells us what is the different amplitude levels that we need to store, and make sure that we have enough such amplitude levels that we have a good way of recovering the signal. So let's say that my orange curve over here had this kind of a behavior. I choose these red lines out here as my possible amplitude values to be stored. What does that mean? It means that the actual value that gets stored would look something like this. I would look at this time instant, find out which is the nearest red line to it, not the orange, right? And store that value, which basically looks like 0, until the next time instant. Remember, I'm quantizing in time also. At the next time instant, I go and look which is the nearest red yellow crossing that I get to, and it turns out it's this value. So the green basically jumps from here all the way up to here. It then goes here. As you can see from this, it is sort of approximating the shape of the original curve, but clearly there is a difference between what the green is showing versus what the original orange curve looked like, right? That's something we live with, right? We basically say that I wanted to discretize in time, I wanted to discretize in amplitude. Once I have done both of those, I end up with what's called a digital signal, right? And this process of converting from this orange curve to this green curve is what is called analog to digital conversion, and it is performed by circuits that are called analog to digital converters, or ADCs, right? So there are a couple of properties of ADCs that you at least need to be broadly aware of, although how exactly they function, how they are built is out of scope, and I'll not be getting into those details. What you do need to know is that, for example, there is some range of values over which an ADC works, which is usually called the full scale range of the ADC. ADCs are usually considered to take an input voltage and convert it into a number. You could have something which is an input current and convert it to a number, but without loss of generality, I'm going to assume that your input is a voltage, right? The principle doesn't change. The ideal ADC, what it says is, I have this range of input voltages and I have a range of output numbers which goes from 0 up to some n max. Okay, what is that n max? I'll have to decide that later. And the ideal ADC, which is shown by this orange line over here, essentially would give the output 0 corresponding to an input of V min. Now, I'm intentionally calling this V min and not 0 because there's no fundamental reason that the minimum input to your ADC has to be 0. It could be negative, right? So it could be that there is a certain range of values across which the ADC works, which get converted in a certain way. You could make a choice that this V min is negative, and for a negative value the ADC returns a 0, or you could decide that the ADC actually has to return an actual 2's complement number so that positive and negative are handled properly, and so on. Or you might say that at the circuit level, I'll make sure that I push everything up so that it goes from 0 to something else and then convert it. All that doesn't matter, right? The point is, there is a certain range of voltages and there is a certain range of numbers. The ideal ADC would actually say, for as I sort of go linearly across this n value that I output will just follow that curve exactly, that straight line exactly. Now this green line that I have instead is something which is intentionally a little bit wobbly, right? What it says is, there's a little bit of nonlinearity. right? It's saying that for certain input voltages, the output code that comes out from the ADC, right, over here is maybe higher than what it should be, because the orange curve is what it should be, the green curve is what it is, it's a little bit higher than what it should be. On the other hand, out here, for example, the green curve is below the orange curve, the output code that I get is slightly lower than what I expect. Now, why does that happen? It's because of the way circuits are built, right? There is some kind of inaccuracy, there is some non-ideality, you can't do anything about it, you have to live with it, okay? So, such things are possible. In other words, this is probably what the possible characteristic looks like. It's not always this kind of a shape, it might be very closely tracking the ideal scenario, or it might be completely off by a much larger amount. It depends on the quality, how well the ADC has been designed and how well you were able to build it and how lucky you got at the end of the day, okay. So, like I said, the output range of the ADC is typically an n-bit value, right, because it's a binary number, which means that if you have n bits and you are treating them as unsigned binary numbers, right, so I'm not worrying about 2's complement and so on, basically the output range becomes 0 as the lowest value all the way up to 2 to the power of n minus 1 as the highest value. Ideally, what we would like is that Vmin gets mapped to the output code 0. Vmax gets mapped to the output code 2 to the power of n minus 1, right, which means that everything else in between is based on a step size. I have Vmax minus Vmin, the total range, and within that I have 2 to the power of n different steps. So, sort of the increment that I can get on each step over there is 1 by 2 to the power of n of this Vmax minus Vin, right. So, to take some concrete examples, right, let's look at the number that n is equal to 10. What that means is the smallest number that I can get is 0, the largest number is 1023. Once again, assume that my Vmin that I am trying to digitize or trying to A to D convert is 0 volts, Vmax is, let's say, 3.3 volts, maybe it's the power supply that's being used for the microcontroller, right. What that means is that your step size is 3.3 volts divided by 1024, which is this number, which is approximately 3 millivolts, right, and this number is called the resolution. So, what this is saying, in other words, is because I had these 1000 steps, I can basically measure some voltage down to an accuracy of 3 millivolts plus minus, right. What that implies is that if I was actually trying to measure, let's say, some electrical signal in the brain or a muscle potential or something, this is probably not good enough, right, because you are talking about microvolts over there. But then the problem that arises is this even the right application, because microvolts kind of voltages have other problems. It's not just an issue of, hey, maybe I need like n equal to 20 over there. That's not good enough, because what ends up happening over there is there will be physical noise associated with the system, there will be noise in your amplifier, there will be noise in your analog circuits, there will be noise, non-linearities or non-idealities in your A to D converter, all of which add up and tell you that, you know what, it doesn't matter if you put 20 bits over there, only 10 of them actually make sense, okay. So, the number of bits is something that you have to choose carefully. It depends on your application, it depends on your signal, it depends on what's called signal conditioning. How well are you able to improve the signal or amplify it before you try quantizing it, right. So, quantizing or digitizing are sort of the same concept, at least over here. Now, a word about sampling rate, right. We already saw that you could take a analog signal like this and convert it into a discrete time signal, and what you can see is there is a certain sampling interval out here. There is a time t between samples that you can see out here, right. And what we usually say is that t is the sampling interval and fs is equal to 1 over t is called the sampling frequency. The question we might ask is, what sampling frequency should I use in order to get a good picture of what the original signal was? And on the face of it, it looks as though, if you keep increasing this fs, that is, you keep decreasing t, you get finer and finer details over here, you will get better capture, right. The problem is you have more numbers to deal with, you get more data to process, right. So, you might say, hey, so what, I can't afford to lose any information, right. Now it turns out that there is a whole amount of theory out there which actually tells you that beyond a point you are not gaining anything by actually sampling with lower and lower intervals, right? And this is called the Nyquist criterion, which tells you that you can sort of understand what kind of frequency content this signal has, how fast is it varying, in other words. And based on that you can then say, okay, this, if I sample at this rate, I will be able to reconstruct the original signal back with a high degree of fidelity or accuracy, right? And if I sample at anything faster than that, I will not get any improvements. Okay, so it's a very interesting result when you think about it, right? And can be used in order to determine what is the rate at which you actually need to sample. And the bottom line is, once you go beyond that rate, you are in the point of diminishing returns. You don't really get any real benefits by sampling faster than that. Of course, practical matters are slightly different. You do need to sample a little bit above what is called the Nyquist rate, but going significantly beyond it does not help. So all of this, in other words, is determined by the signal characteristics, which means that it's not as simple a problem as saying, hey, I'll take the fastest possible ADC that is available to me and use it. You need to choose an ADC which meets your requirements. You need to understand the signal that you are working with and choose an ADC that is good enough and at the same time provides you with enough information that you can perform useful computations with it. So what happens when you are actually trying to put an ADC, activate an ADC in a microcontroller? It turns out that for the STM32, for example, you can actually choose, right? Unless you explicitly activate and say that, this pin is going to be treated as an A to D converter, only after I select this particular IN4 over here, does this thing, the PA4, basically turn on and say this is going to be ADC1 underscore IN4. Meaning that I can connect an analog signal to this pin now and then write code inside the microcontroller that will sample that. Okay, by default, all pins are not considered active for analog. I can't really activate them. I need to explicitly turn them into analog mode so that I can use them, right? Or I need to have some kind of setting by which I can actually activate the analog mode and activate the ADCs for sampling. Now, it turns out when you look at this thing out here, you will find that there are a whole lot of different parameters that need to be set for A to D conversion, right? There are many terms you will come across. I'm going to be touching on very few of them over here, right? What you actually need to do is actually look into the ARM reference manual for the STMicro series and go through those in order to really understand how to use the ADCs to their full capabilities. Examples of the settings that you need for different ADCs are for something like the prescaler. We already sort of briefly saw the prescaler in the clock settings, and what it basically says is that it allows the ADC to work on a clock which is a divided version of your master clock, right? You can sort of go down to a slightly lower frequency which is more suited for the sampling rate that you want and then use that for your sampling. You can also configure the resolution. You can say you want it to be either 12 bits or 10 bits or 8 bits. Now you might wonder why I would want to change that, and it turns out that the kind of ADCs that are actually used over here are very often something called successive approximation ADCs, right? Meaning that they take more time to convert a 12-bit number than to convert to an 8-bit number, right? So you could potentially do faster sampling by just going for 8-bit values if that is good enough for you, right? If you find that your signal only requires 8 bits of resolution, there's already too much noise in it, going to 12 bits is not really giving you useful information, fine, just stick to 8 bits and it will probably finish the conversion faster and consume less power and consume less area, because storing 8 bits requires fewer memory locations than storing 12 bits per sample. There is also implicitly some kind of alignment that you can do, which is the interesting thing is, supposing you actually have only 10 bits of data, when you actually read it into the register inside the microcontroller, you don't have a 10-bit register, you either have a 16-bit register or a 32-bit register, and you can sort of implicitly give it instructions for what alignment to use, right? Now it might seem obvious that right alignment is the way to go, which is that you just take your data, put it in the LSB bits of the signal and just sort of pad it out with zeros. Now okay, that's alright if you are just trying to deal with it as a number. The problem is, what about, if you are dealing with positive and negative numbers? If your ADC had a plus and minus range, then there should not really be zeros, it should be a sign extension of what you have out here. The alternative is what's called left alignment, where I could do something like this, where the important bits, the actual ADC bits, go into the left part of the data, right? Once again, these are options that you can use in order to tune the behavior. What is probably most important as a designer is that you need to choose the right resolution for your system. The other things are more sort of secondary, in the sense that they are more in terms of tuning the behavior of your actual performance of your system. One other sort of important concept to keep in mind in the context of ADCs in a microcontroller is that typically you have what are called multiple channels, right? And the idea is that you use a single analog to digital converter, but it has multiple inputs, right? And these inputs can basically get multiplexed into the single ADC, and what the ADC can then do is it can quantize in 1 or in 2 or in 3, depending on which channel you have chosen. So by just having one physical piece of hardware and one multiplexer, I can perform conversion of multiple different signals. Now the flip side is that there are a couple of things that happen. One is, let's say that there was a temperature and humidity and moisture value that I wanted to sample. Because of the fact that they are being multiplexed like this, there is no way that I can get all three of them at exactly the same time instant, right? Because I'll first have to convert this, and then this. And what that means is there is going to be some time taken for converting in 1, after which I can start converting in 2, after which I can start converting in 3. Now, especially in applications where your sampling rates are fairly low, right, this may not matter, because the time between samples is probably on the order of milliseconds, and this time for sort of switching between one to the other is probably in the microseconds range. So you don't care, it's fast enough. But for applications, for example, like software defined radio or other things where your sampling rates themselves are very high, the difference in time between different samples might be on the same order as the sampling interval itself, which means that the time instants at which you are getting your data are actually sufficiently different that you need to compensate for that in your algorithms. Now that's as far as the sampling itself is concerned across channels, but there are a lot of settings that you can use. One of them is what's called a scan setting, which basically says that the microcontroller can be configured to automatically scan across channels one after the other, and the moment I ask it to convert in 1, it will then immediately go on to in 2 and then in 3 after it has finished in 1. I can also use the sequencer in order to determine the sequence in which to do this. It could do in 1, then in 3 and then in 2 and so on. You could change that around. And yet another thing that can be done is you can go into what's called continuous mode sampling, right? To some extent, the picture that I've been showing all this while, where I'm just taking a signal and digitizing it in into small steps, is continuous mode sampling, where I want a large number of samples of a signal. But I might also have what's called just event based sampling, right? Maybe once in every second I just want to see what the temperature is like. That's not really enough data to find out the fine grained variations in temperature, but maybe it's good enough for what I have in mind, right? So if that is the case, then I don't do continuous sampling, I just sort of do event based sampling. Maybe I set a event which wakes up my microcontroller once every second or once every minute, looks around, samples all my sensors, sends them off somewhere and then goes back to sleep. Okay, so continuous sampling would basically say, as soon as I have finished sampling something over here, go back and sample it again. Of course, if there are multiple channels, then finish all of them and then go back to the first one and repeat. But obviously that's going to consume a lot of power and may not be what I want in the first place, right? So you can basically change that around. Now there is also a notion of what's called the sample and hold circuitry inside an ADC, which is basically saying that you have a signal. Before you can convert it into a number, that takes a certain amount of time, the conversion, because there is some circuitry which actually goes through a few steps in order to convert. So what do you do? During that time the signal might change. To prevent that from happening, what you do is you briefly close one switch over here, let that signal come onto this capacitor and then open the switch again, right? And the idea is once you have opened this switch, this capacitor will just hold the last voltage that it saw from here. It will hold that value for a certain amount of time, and that is what is used for conversion. And by sort of just closing opening, you are able to sample the signal at different time instants and make sure that those different values are the ones that get converted into numbers. Okay. Longer sample and hold times give you usually better conversion because it gives a better chance for this capacitor to exactly take the voltage that you have here. But it also means slower conversion rates because you have to wait for a certain amount of time and then do the conversion. So for very high speed applications, you don't have long sample and hold. You need to keep this as short as possible. But at the same time, you want it to be such that the conversion also happens in a meaningful manner. So once again, the sample and hold parameters are things that can be controlled using the different settings that are there in the configuration of the ADC. And one of the more important questions that you need to answer as far as A to D conversion is concerned is, when should I start? Or rather, when should I do a conversion, right? Like I said, you could have an automatic conversion process, which is typically what you want when you're taking a real-time signal and trying to convert it into something. That's when things like Nyquist rate and so on come into the picture, right? You sample, you convert, and repeat this process. That's it, right? As soon as you have finished a conversion, you basically go back and repeat with the next sample, right? So you then choose something which is more or less sampling at a high enough rate that you get high fidelity reconstruction capability for your signal. It also means higher power consumption. It means that you are sampling the signal at whatever your rated system speed is. On the other hand, like I said, you might basically have something that is triggered, which could be either an explicit request from software, right? At every now and then, your software basically says, hey, read an analog value from here, and the system basically goes, triggers an analog to digital conversion and gives you back a value. And the alternative would be to basically say, okay, I have some kind of a event that is generated perhaps by a timer. So there's a timer which basically automatically generates some kind of a signal once every second or once every minute, and based on that, my analog to digital converter kicks in, performs a conversion and gives me a number. So how you trigger the conversions is also something that can be controlled from software. So to summarize, what is the purpose of ADCs in the first place? Interface with the physical world, right? Because the majority of physical real life signals are analog. We have various kinds of sensors that can take those analog signals and convert them into voltages. And then I need to take those voltages and convert them into numbers. Right? There are many parameters that you need to be aware of an ADC. One is the resolution, the other is the full scale or the full range of conversion, the maximum sampling frequency. All of these are properties of the converter and also are determined at the end of the day based on what kind of signal you are trying to convert. They are very common in MCU applications, right? You can, in the context of MCUs in particular, there are specific ideas such as the multi-channel values, multi-channel signals, and sequencing across channels and triggering that you need to be aware of and need to keep in mind while designing systems with A to D conversion. So here what I am showing is an example of how we can use the Arduino type of coding, not the basic C-level coding, in order to read an analog value, right? And I just want to sort of use this in order to illustrate a couple of different things. One is how you would go about, once again, something like the analog pin PA0. This is one of those parameters, right? The hardware abstraction layer takes care of it. It tells you that you can use this number, this token PA0, in order to indicate this particular pin, the A0 that is to be used for the sampling. The setup part of your code basically says two things. One is it sets up a serial communication by straight away just using the serial interface and saying begin at 9600, right? Now, part of the reason why in this course I'm going to be looking a lot more at other examples where we go into more details of the C code, right, is because the Arduino kind of interface abstracts away a little too much sometimes, right, and we'll look at specific examples of that later. On the other hand, I will also be using the Arduino type of code because it allows us to get a good feel for what are the ways of using the different interfaces on the microcontroller in a very simple and straightforward manner. So what is it that the Arduino has done, Arduino type of code has done over here? It allowed you to basically just initialize the serial port. You don't need to worry about which pin it is connected to, you don't need to worry about the settings on the pin, you don't need to worry about how to initialize those pins into output mode, what pull up and so on, if at all required, right? All of that is sort of hidden behind this one function call. But what it has done is, it sort of also implicitly assumed that you wanted 8 bits, no parity, 1 stop bit, okay, which is the most common kind of scenario, but it didn't really give you an option at all over here, it just assumed that that's the default. Now that's great when you are able to work with defaults. When you want to work with different settings, it becomes a little bit more difficult, and you will often find that in order to get the best functionality out of your MCU application, you can't really stay with the Arduino style of code. You need to drop back into a version which allows you finer grained control over the different settings. For now, I'm just using this to demonstrate the how to communicate with the peripheral in the first place. So I'm going to leave aside this and use the easy to explain code. The pin mode analog pin input. What's analog pin? It is this hash define that we had out here. I'm using input as a token into this pin mode function, which would ultimately behind the scenes go in and basically write into some settings register in my GPIO port and say, hey, this particular pin which corresponds to PA0 should be configured in analog mode, which means that the ADC needs to be set up, the sampling frequency for the ADC needs to be set up, whatever the mode of conversion, lots of defaults basically need to be set, all of which get hidden behind this one function call, right? Then what do we do in the actual loop? I simply go ahead and say analog read. What does this do? This is an actual trigger. This is the trigger event, right? So unlike a continuous mode conversion where I basically say, hey, I turn on the ADC and it just goes into continuous mode, this is saying this is software triggered. Only when I call this function analog read will it actually write some value into a particular register which triggers the analog conversion, wait a certain amount of time, get back the value from the register, convert it into a number for you, and finally put it into this register called ADC value, right? And the good thing is over here, all that we really care about is, can I print that value out, can I look at it, right? And finally what I do is I put in a small delay between readings just to sort of make it easy to read what's going on. I wait for 1 second between readings. So what does my circuit itself look like? What I've got here is a model of a potentiometer, a circular knob, which as I turn this around I should find that the voltage that is going into this A0 pin varies between what I have over here, which is the ground potential, which is connected using black to this GND pin, and this red wire, which is VCC, which is 3.3 volts. This potentiometer signal, right, the green wire, is connected to A0. What this means is, at any given point in time, as I turn this, right, by clicking and turning around on it, when it's at the leftmost point, it's basically going to send a voltage of 0 volts on the signal. At the rightmost point, it will send 3.3 volts, and somewhere in the middle, it will send 1.5, 1.65 volts, right, which is halfway, and all the values in between. What my A to D converter should do is, every time I run the analog read, it will sample the value that is seen on A0, convert it into a number, and print it out onto the terminal. So let's run this, right? When I run this, you can see that yes, it's printing out ADC value 0, 0, 0, and you can see that there is a 1 second pause between values. What I can do is I can basically click on this and slowly drag it upwards, and you can see that the numbers start changing, right? You can see that it's going up and up and up, and when I reach somewhere near the top, it has come close to 500, right? And as I go all the way and pull it to the other extreme, now I find that when I go beyond that, it basically sticks at this point, and the value has become 1023. Why? Because by default, what this has done is, it has done an 10-bit conversion of the data. So the range of values between 0 to 3.3 volts was converted into a number between 0 to 1023, which is what is coming out depending on the value from this potentiometer, right? And as I change it, when I go roughly halfway, I find that the output becomes 508. Exactly halfway would have been 511 probably, right? But you know, that depends. It's an analog value. I'm not able to control it that well out here, but it's close enough. Okay. So this is just a demonstration to show you two things. One is how exactly the communication happens, how the triggering of the analog conversion happens, and more importantly, the fact that the Arduino sort of hides most of that complexity, the Arduino style of coding, the sketch style of coding hides most of that complexity from you, right? You basically just call the analog read function and the pin mode function that has automatically set up the A to D converter, activated it, set it to 10-bit mode of conversion, right, and is also set to manually triggered. So all of these things have sort of been either done explicitly as part of one of these functions or are the default values that are present in the system, right. It obviously makes your life much easier in terms of how you use it, but it has its own drawbacks if you think about it from the point of view of what level of control you can get. If you wanted, for example, to increase the serial speed, or if you wanted to change this to 12-bit values, it's not so straightforward to do it using this kind of code, and you would find that you need to fall back to the regular C code in order to get that level of control.